So any questions from previous class before we begin the today's class? Okay. So in the last class, we were discussing about the possible effects of the groundwater. So we little try to understand what would be the possible consequence if there is a change in groundwater table on the bearing capacity. However, we didn't quantify how uh, the increase or decrease in bearing capacity can be calculated. So let us try to understand. So if there is a change in groundwater table, then how it impacts the value of the bearing capacity. So here in this picture, four different cases have been shown, where in case 1 the groundwater table is at ground surface, in case 2 where the location of groundwater table is between the foundation level and the ground surface, in case 3 the location of the groundwater table is right at the foundation level, and in case 4 it is below the footing. So these are the four variety of cases that possibly we encounter. So when you try to deal with any bearing capacity calculation. So case 1, when the groundwater table is at ground surface or groundwater table coincides with the ground surface. Case 2, it lies
Sir,
in between. Yeah.
sir, are you sharing something?
Oh,
It's not visible.
okay, okay. Is it now?
Yes, sir, it's visible.
Okay, thank you. Sorry. Yeah, so this picture shows in how many ways the groundwater can impact the bearing capacity. So first, let us take case 1 where the location of the groundwater table coincides with the ground surface. Case 2, the location of the groundwater table is between ground surface and the foundation level. Case 3, the location of the groundwater table coincides with the foundation level. Case 4, the location of the groundwater is below the footing level. So first case 1, where the groundwater table coincides with the ground surface. So in this case, suppose if you look at the bearing capacity equation, there are three terms. Q ultimate is nothing but CNC plus QNQ plus of gamma B and gamma. So this is second term and this is the third term. While the first term is C and C. So this is called as a cohesion term. But here uh, there is there is no term related to the density. But in the second and third term, that is overburden and the self weight component, if you look at carefully, in these two terms, there is a parameter called as a density gamma. So as we have understood from the fundamentals of the soil mechanics, when you talk about the density, you can talk about the bulk density, dry density, submerged density, so on and so forth, depending upon the moisture condition or the groundwater table condition. So accordingly, when the groundwater table rises to the ground surface or it lowers, depending upon its position, you should manifest the same effect in the form of this gamma value. This gamma value. So in case 1, where the groundwater table right at the ground surface, then use gamma dash use gamma dash for gamma df nq and of b gamma b and gamma. So in both these parameters, replace bulk gamma with submerged gamma, because the first gamma is pertinent to this location, while the second gamma is pertinent to below the footing. So both above the foundation level, this dotted line itself is a foundation level, below the foundation level. In both these cases, the groundwater table exists above these two surfaces or above these two levels. So therefore, herein the submerged density prevails, while below the footing also submerged density prevails. So therefore, in case 1, in the whole equation, wherever gamma is appearing, the same gamma shall be replaced with the submerged unit weight, that is gamma dash. Next, case 2, where the location of the groundwater table is between ground surface and the foundation level, that is dotted line. So in this case, uh, the height from the ground surface to the foundation level. So this is ground surface to the foundation level. So half is the dry density prevails, and below half, which is an height equal to HW, so submerged weight prevails. So accordingly, you can take something like gamma df, where gamma is above the groundwater table, and gamma w, that is gamma submerged, can be taken below the groundwater table. So, but here the impact is again on the second term, while on the third term, so that is of gamma b and gamma, the gamma shall be replaced with the submerged, while in the second term it will be summation of above the groundwater table and the below the groundwater table. Above the groundwater table it is a bulk density, and below the groundwater table it is submerged density. So it is combined effect. So that is case 2. Case 3. So here also there is a specific. Suppose if you look at, again there are two terms in our case, gamma d and q plus half gamma b and gamma, as I have highlighted here. So the second term is pertinent to above the foundation level, while the third term is pertinent to below the foundation level. And the groundwater is right at the foundation level. So above the foundation level, the soil is dry. So therefore, your gamma will be gamma bulk. While below the foundation level, so it is submerged. So therefore, gamma will be replaced with the gamma dash. So this is case 3. And the last case, that is case 4. Case 4. So here it is at a depth of df plus d from the ground surface. So in this case, use gamma for the second term, that is gamma df and q, and same as of gamma b and gamma. That means in case of the case 4, where the groundwater table is at a depth of b from the foundation level, or df plus b from the ground surface, there was no impact of groundwater on the bearing capacity. If you look at carefully, use gamma for the gamma df and q and half gamma b and gamma terms, meaning thereby in case 4, where the groundwater table is at a depth of df plus b, there is no effect of groundwater on the bearing capacity. So what if groundwater is between ground surface and above df plus b, or below the foundation level? So in that case, you need to interpolate the values of gamma. So this is the case. So this is another case where the groundwater is located at a depth of d from the foundation level, at a depth of D from the foundation level. But this D is less than B. This D is not equal to B. If D is equals to B, there is no impact of groundwater on the bearing capacity. But suppose if D is less than B, then you have to use in the third term gamma bar, that is gamma dash plus D by B into gamma minus gamma dash. So this gamma dash shall be used in place of gamma of gamma B and gamma. So this is how one can able to account for the effect of the groundwater on the bearing capacity. So which otherwise there is no change in the values of the NC, NQ or N gamma or any other parameter. So the impact of groundwater is accounted for in the form of only by changing the gamma value, that is density of the soil. So anybody has any question in understanding the impact of groundwater? Any questions? Okay. So that's what the effect of the groundwater. Now, if you recall the entire discussion on the bearing capacity calculation, so we were discussing about different equations. One is Terzaghi's equation, Meyerhof equation, Visick equation, Hansen equation, so on and so forth. So, but these equations are called as a analytical equations, meaning thereby they were derived based on some fundamental concepts, based on say for example active earth pressure or passive earth pressure or any other assumption which were made by the corresponding researcher. But that is not an realistic, because these are analytical equations and are based on some assumptions. But how to verify that the bearing capacity which was calculated based on the analytical equation is true or not? So for that purpose, we need to verify the calculated bearing capacity equation by conducting a test called as a plate load test. Plate load test. So this is one of the in situ test that is conducted directly on the field. So therefore, whatever the bearing capacity value that we obtain will verify whether it is correctly or not reflecting the Q ultimate calculated by using the analytical equation such as Terzaghi's equation or Meyerhof equation or Visick equation or Hansen equation. So this is the whole setup of the this is the complete setup of the plate load test. As you can see, so this is typically comprises of, so this is the original ground level. So this is the ground level. So there is a small pit is excavated below the ground surface, small pit, and at the middle of the pit, a small plate is used. A small plate having a size square or circular, whatever it is, of the size of 30 centimeter or 60 centimeter and a thickness of about 2.5 centimeter. So on this plate, a load of uh, above the ultimate bearing capacity is applied. But the entire crux lies in how do you apply the dead load on the bearing plate. So the dead load applied, so with the help of the sandbags, so these are all sandbags accumulated on one kind of the platform. Here you can see this is a steel joist which acts something like a platform or a beam, and this is embedded or installed in the ground on either side of the pit. Above these steel joist, a huge dead weight in the form of a sandbags or in the form of a concrete blocks or in the form of a stones. So they will be placed. The de- the dead weight of the sandbags is higher than the ultimate bearing capacity of the soil mass. Now it is bit difficult to understand how it could be above the ultimate bearing capacity of uh, the soil. So for that purpose, you need to calculate analytically Q ultimate value, and based on that you need to calculate what should be the dead weight required. It is like, suppose if the ultimate bearing capacity is say X, the dead weight should be X multiplied by some factor, say 1.5 or 2 or 3 depending upon the codal provisions. Now this steel joist which is hosting the dead weight and the bottom plate, either that is 30 or 60 centimeter diameter, which is a round or a square, doesn't matter. In between, a hydraulic jack is placed as shown here. So the principle of this hydraulic jack is very similar to the test which you have conducted in your laboratory. Say for example, when you have done the compressive strength of a concrete block or brick, so you have used one kind of a compressive strength testing machine. So the operation of this hydraulic jack is exactly similar to such a machine. So this jack is connected with a dial gauge which indicates how much pressure has been applied. While on the steel plate, dial gauges, another set of dial gauges are placed which measures how much amount of the settlement. How much amount of the settlement. So let me give further details how this test will be conducted. So this is the realistic picture of a plate load, as you can see. So this is the schematic. So this is schematic. So there are set of dial gauges. These dial gauges are used for measuring the deformation. So you can see a set of dial gauges, and this is the plate I'm talking about. So here it is more than 30 centimeter diameter. Onto this plate, a huge amount of load is applied. However, the application of the load is not instantaneous, rather it is very progressive. Now, so these are a few steps which shall be followed for conducting the plate load test. First, you need to excavate a pit of size 4 to 5 times the size of the plate as shown here. Suppose if BP is the width or diameter of the plate, you need to excavate a pit of a size equal to 5 times. 5 times the diameter of the plate approximately. And what should be the depth? What should be the depth of the pit? The depth of the pit supposed to match with your depth of the footing, that is DF. And this DF you have decided based on your analytical calculations. So it could be 1 meter, 2 meter, whatever the depth of foundation that you have fixed it. So the depth of the pit is equal to the depth of the foundation, while the width of the pit is equals to 5 times of the width of the plate. For example, if the width of the plate is 30 centimeter, so then the width of the pit is 150 centimeter. So this is called as a bottom of the pit should coincide with the level of the foundation. So there may not be a constant value of the level of the foundation. It depends upon your design. In case if the groundwater table is exist above the ground surface, then you need to lower down the groundwater table by the pumping phenomenon. And so this is the plate size. So once this whole arrangement is done, then you need to apply the load using the hydraulic jack. You need to apply the load using this hydraulic jack such that the rate of loading is, or the rate of settlement is 0.25 millimeter per hour shall be achieved. So using this hydraulic jack, you need to apply the load such that the rate of settlement shall be 0.25 millimeter per hour. Now here this may or may not be achievable because we do not know any condition. So therefore, if you do not know this one, then you have to apply some amount of the load, or the load increment shall be approximately 1/5 of the estimated safe bearing capacity of the soil. Now, from where did you estimate this safe bearing capacity? That is from the analytical equations like Terzaghi, Meyerhoff, Wisick, and Hansen. Suppose if you take an example, suppose you have calculated the load as 1000 kilonewton. So then initial load increment will be 1000, 1/5 of the 1000, say 200 kilonewton. Then next increment is another 200. So 200 plus 200. Net will be 400. So then 600, then 800, then 1000. So this is how you need to increase the load. But how long shall I maintain a particular loading condition? For example, initially I applied 200 kilonewton load. How long shall I maintain the same load? So you need to maintain that load until such time when you are measuring the settlement at the bottom of the plate using these dial gauges, where the three consecutive dial gauge readings shall be remain same. That means there is no more settlement is happening because of that imposition of that particular load. Okay, once you recorded that three consecutive settlement readings are same, then you should go for the next increment of load. And that load shall be maintained until three consecutive dial gauge readings are remained same. So this entire process has to be repeated. Now when you repeat the entire process, you will get a curve, that is plate bearing pressure versus the settlement of the plate, and this is the relationship between the load versus settlement. So either you can convert this into stress strain or typically, but this is called as a plate load test graph. It's always plate bearing pressure versus the settlement in millimeter. So there are some other guidelines also. At what time shall I stop the test? So there are two variety of guidelines. One guideline is you should end the test as and when you are achieving the desired settlement depending upon the foundation type. For example, you are using the isolated footing, where for isolated footing the permissible settlement is 25 millimeter. So once you are achieving the 25 millimeter, then you should stop the test. You should stop the test or stop applying the load and terminate the test. Or alternatively, suppose if you are planning for say combined footing or the mat foundation, then your settlement value will be different. So maybe 50 millimeter or maybe 75 millimeter. That means you need to impose the load until you are achieving the 50 or 75 millimeter of the settlement. Now alternatively, sometimes even before accomplishing the desired settlement of 25 millimeter, the soil fails under shearing condition. So therefore, you need to continue the plate load test under two circumstances. One is until you are achieving the desired settlement, or alternatively until the soil is failing under shearing condition. Whichever happens first, at that state you need to terminate the plate load test. So at the end of the plate load test, what we get is a relationship between plate bearing pressure versus settlement of the plate. So here, now which one shall I pick it? Shall I rely based on the settlement, or shall I rely based on the bearing capacity? Suppose if you look at the IS code on conducting the plate load test, and depending upon your footing type, that is isolated footing or strip footing or wall footing or combined footing, so pick the value of the settlement. For example, in this case, my permissible settlement is 25 millimeter. So corresponding to 25 millimeter settlement, so draw a horizontal line onto the graph, and from there draw another vertical line onto the x-axis, which gives what should be the allowable the bearing pressure on the soil. So this is how the allowable bearing pressure by resorting to the plate load test will be determined in the field. Will be determined in the field. Now, depending upon the soil type, we may not always get a unique type of the load versus settlement graph, as you can see in this picture. So for example, if you are conducting the plate load test on cohesive soil, you will get the load versus settlement something like this. So initially some resistance is offered by the clay, then thereafter there is a continuous settlement even without increasing the load. While in case of the loose to medium cohesionless soil, that is sand, so there is a reasonably increase in settlement with increase in the load. Similarly, partially cohesive soil also, there is a continuous increment in the load with increase in the settlement, or vice versa. In case of the dense cohesionless soil, so it is there is up to a certain extent there is an increase in the settlement with increase in the load, and thereafter it became a constant, or there is a continuous increment in the settlement without increment in the load. So based
So
on
are these failure points means this is failure position.
this is not a failure position, because this point is where the settlement is excess. Failure means the test will be terminated. For example, if there is a breakage, then the graph suddenly terminates here. There is no further continuity. Okay. Suppose if there is a failure in the soil, there is a sudden abrupt termination of the graph. So which otherwise you can continuously record the settlement even if there is no increment in the load. But see, if you look at these four graphs, all four graphs are unique. Then how shall I interpret the ultimate bearing capacity of the soil? For example, if you look at curve B and the curve D, it is quite easy. So you simply draw a vertical line onto the x-axis. Wherever it is meeting, then that shall be taken as the allowable bearing pressure on the soil in both these cases. While in case of the A and C, it is bit difficult to interpret what shall be the ultimate bearing capacity. Now here we can follow two school of thoughts. First one is, you suppose if you look at the curve C, there is a kink at some point. So it is somewhat like a bilinear in nature. So what you need to do is draw two tangents to this graph, wherever these two tangents are meeting, that can be taken as the ultimate bearing capacity of the soil, or the allowable bearing capacity of the soil. Similarly, so in this case also, you try to draw two linear tangents for the initial portion and the final portion. So the intersection would give you the allowable bearing pressure on the soil sample. So this is the guidelines given by Bureau of Indian Standard Code 188/1982. So this is how this is some kind of a guideline on interpretation of the ultimate bearing capacity of the soil based on the plate load test. Now there are some other equations also given by the same code. Uh, those equations, how shall we use? Now let us try to understand. We are conducting the plate load test using a plate of width either 30 centimeter diameter or 60 centimeter diameter. But ultimately what we construct on the soil is a footing. So we are not going to put the plate on the soil. We are going to put the footing. So then how shall I convert the plate bearing settlement equivalent to the footing bearing settlement? So depending upon the soil type, suppose for example, you are dealing with the sand. You have conducted plate load test on sandy soil. Then you should use this equation for calculating the probable footing settlement based on the plate settlement. Similarly, in clayey soil, if I know the settlement exhibited by the plate, then I can able to calculate the possible settlement to be exhibited by the footing. So here if you look at SF designates permissible settlement of the foundation in millimeter. SP is settlement of the plate in millimeter. So SP will be obtained from the plate load test. So which is again used to anticipate what would be the probable settlement exhibited by the footing. So these are the two independent equations. The above is for the sand and below is for the clayey soil. So this is a very simple test. Anybody has any question? So these are some important points about the plate load test. Since a load test is a short duration, so these are very important points. So everybody must understand this one. So in yeah, please mute yourself. So some important points are, see for example, when you construct a footing, so it is going to be forever. But the plate load test is conducted only for a very short duration. The entire plate load test will be done in 24 to 48 hours. So based on this 24 or 48-hour test, we have to predict the settlement exhibited by the footing that will be there forever. So since the load test is of short duration, consolidation settlements cannot be predicted. Now, as we know from our soil mechanics concepts, consolidation is a long-term phenomenon that could happen over years, not in terms of the days. So therefore, your plate load test shall not reflect the consolidation settlement. It can only reflect the immediate settlements. So it gives only the immediate settlement, and hence if the underlying soil is a sandy in nature, so then S immediate can be taken as S total or S plate, because in case of the sand, there is no consolidation settlement that could happen. So therefore, whatever settlement happens, they are immediate settlement. So if the soil is clayey type, the immediate settlement is only a fraction of the total settlement. That means, so the plate load test settlement cannot be used for calculation of the settlement of the clayey type of the foundation. It shall be taken as only the fraction. Hence, load tests do not have much significance in clayey soils to determine allowable pressure on the basis of the settlement criterion. So plate load test is not recommended in soils which are not homogeneous at least to a depth equal to 1.5 to 2 times the width of the prototype dimension. So if the soil is a too much of variation in the strata, then you should avoid conducting the plate load test on such soil. So this test is preferable only on homogeneous soil type. So
Sir,
plate
what is
load
mean by width of prototype foundation?
width of prototype foundation means, for example, your width of the footing is 2 meter. Okay, so the total depth of the homogeneous soil will be 2 multiplied by 2. That means up to 4 meter you need to have a 4 homogeneous soil. Up to depth of 4 meter you
Okay.
need to have homogeneous soil. Plate load test should not be relied on to determine the ultimate bearing capacity of the sandy soils, as the scale effect gives very misleading results. Now, scale effect means something like prototype foundation. Prototype means this is a real life foundation. Say for example, the real life foundation is 2 meter width. 2 meter width. But when we have conducted the plate load test, we did use only 0.3 meter plate. 0.3 meter plate. So suppose if you do a plate load test using the 2 meter foundation and using the 0.3 meter, it is obvious that the results are completely different. So this is called as a scale effect. The difference in geometry between the prototype foundation and the plate is called as a scale effect. So this 0.3 meter is called as a model, while the realistic footing size of 2 meter is called as a prototype. So this is called as a scale effect. Okay, however, when the tests are carried out on clay soils, the ultimate bearing capacity as determined by the test may be taken as equal to that of the foundation, since the bearing capacity of the clay is essentially independent of the footing size. Okay, so from this point it is quite clear. In case of the sandy soil, the bearing capacity is dependent on the footing size, while in case of the clay, the bearing capacity is independent on the footing size. Therefore, the plate load test bearing capacity values are valid in case of the clay, while the settlement values are valid in case of the sandy soils. It is a bit contrasting. Okay, so but this is the most important observation that you must note down. So that's what about the plate load test. So it is one of the simple test and easy to understand. But so these are some important point that you must understand and remember. So these are some other understanding about the bearing capacity, some of the terminology that you need to keep it in mind for your entire life. So for example, we talked about couple of terminology, ultimate bearing capacity. Then there is another term called as allowable bearing capacity. The ultimate and allowable, let me explain you. Ultimate means it is the maximum amount of a load the soil can able to bear. Now when I say the maximum, the moment I apply the ultimate load, the soil undergoes shear failure. That's for sure. Okay. But when I say the allowable, Q allowable, what is that allowable? Here the allowable is the settlement. Allowable is settlement. Okay. So if I use the allowable value, my settlements are within the permissible limit of say 25 millimeter or 50 millimeter or 75 millimeter. So that's what is. Q ultimate means it is the ultimate load borne by the soil. So behind Q ultimate, the soil fails. Allowable means so it is the load at which the settlement can be achieved is the 25 millimeter or permissible settlement within the permissible settlement. Next, FS is factor of safety. Usually for bearing capacity, we use a factor of safety of 3. However, this is only valid for the soil. Suppose if you take in case of the rock, the factor of safety up to 8 can be used in case of rock. Okay, so you must remember. So the value of the factor of safety is not remained same. And again, the factor of safety is dependent on different things. Soil type, as I told, soil, rock, I try to distinguish. Then structure type, soil variability, then extent of the site characterization. You must keep all these 4 things into account or in mind when you decide or take the value of the factor of safety. You should never ever take a constant value of the factor of safety. So you should give enough thought. So then, so there are some other equations like uh, in your soil mechanics, you also understood about drained condition, undrained condition. So for example, what will happen to the bearing capacity if there is a water? What will happen to the bearing capacity if there is no water? If there is a water, that is called as a undrained condition. Undrained, the water exists in the soil. In that case, the ultimate bearing capacity can be calculated as NC dash into SU. So in case of the undrained, so the value of the NC star can be taken as 5.14 for strip footing, 6.14 for square or circular footing. Now another important thing is that when you talk about undrained, the soil will not show any kind of the friction. That's what is the meaning of undrained in this slide. Okay, and the same thing you can observe. So in couple of the tables pertinent to Terzaghi's theory or Meyerhof theory, I specifically emphasized when pi is 0, the value of the NC is 5.14 and NQ is 1 and N gamma is 0. And these values you must remember. So that means when pi is 0, that condition reflects when pi is 0, that condition reflects the undrained situation. Undrained situation. And in case of undrained situation, you should use the Q ultimate is equal to NC star into SU, where NC star is 5.14 or 6.14, depending upon the shape of the footing. And SU, the value of this is called as the undrained shear strength of the soil, so can be taken as within a depth of 1b to 1.5b beneath the foundation, and you can use this equation for calculation of the undrained shear strength. So here instead of using this equation, most of the time people use SU as equivalent to the cohesion, so that is also valid. Then in case of the drained condition, because the previous slide is talking about undrained, in case of the drained condition, we can use this equation. Q ultimate is of gamma dash B and gamma. So where N gamma star is a foundation shape, the function of the foundation shape, and pi dash.
Sir, what is SU in last slide?
This is undrained shear strength of the soil. Undrained shear strength of the soil. Okay. Okay, yeah. So in case of the drained condition, you should use this equation. So here N gamma star is a function of the foundation shape and pi dash. So here it is related with the effective stress friction angle pi dash. So try to understand the difference between drained and undrained is, in case of the drained, every terminology is in the form of a effective stress. But when you talk about the undrained condition, all terminology is pertinent to the total stress. Undrained means total stress analysis. Drained means effective stress analysis. Okay, so this is how you should get the N gamma star. And so here you can see there are two predefined curves. One is for the strip footing, next is for the square or circular, depending upon the angle of internal friction. Then you shall pick up the value of N gamma star. So when you try to deal with the different soil types, suppose when you are dealing with the sand cannot hold lot of amount of water. The moment you pour the water, because of its hypermeability, all water gets drained out. So therefore, in case of the sand, perform drained analysis. In case of the clay, perform both, because in case of the clay, the permeability is so low and the consolidation phenomenon prevails in case of the clay, and this consolidation is a function of the time. So it can occur over a period of 1 year or 2 years or 3 years or 5 years. So as the consolidation progresses, the stress condition transforms from undrained to the drained condition. That's why you need to conduct both undrained test as well as drain test in case of the clay. So usually a factor of safety of 3 is used, and these are the steps that you can follow. So then you have to calculate the Q ultimate. So these are the steps only. So in the previous, it is straightforward. So let us discuss about it. So our aim is to calculate the Q ultimate. So then we should consider either drained or undrained conditions and methods for obtaining the over consolidation ratio and pi dash. So for that we can use the soil exploration techniques data, that is cone penetration or standard penetration. So any kind of data can be used for obtaining the Q ultimate. So alternatively, so we can also give importance to, so for example, your aim is to calculate or design the foundation rather than determining the ultimate bearing capacity of the soil. So then you can go in a reverse way. So you know the ultimate bearing capacity of the soil, then you can by back calculating, so you can fix the width and depth of the footing. So other conditions like foundation safe, whether the foundation or the footing is subjected to the only axial load or moment and axial load, so on and so forth. So these are some important points about the bearing capacity. The ultimate bearing capacity and settlement of the footing on sand increases with an increase in width. So meaning thereby, in case of the sand, the bearing capacity and settlement both depended on the geometry of the footing, that is width. In other words, for a given settlement, the corresponding unit soil pressure decreases with an increase in width of the footing. So this is what we have seen. So as we go deeper and deeper, there is more and more area gets spread the same delta sigma. So it is therefore essential to consider that settlement will be the criterion for the design of the footing in sand. This is most important. So when you are dealing with the bearing capacity in sandy soils, you should take settlement as the criterion for design of the footing. So experimental evidence indicates that for footings smaller than about 1.2 meter, where the width of the footing is less than 1.2 meter, the allowable bearing pressure Q is the criterion for the design of the footing, whereas settlement is the criterion for footing greater than 1.2 meter. So, so when you are dealing with the sand, so if your footing size is less than 1.2 meter, give preference to the bearing capacity. If the footing is above 1.2 meter, give preference to the settlement. Similarly, in case of the clay, bearing capacity of footings on clay is independent of the size. And as such, the unit bearing pressure remains theoretically constant in a particular environment. Settlement of footing increases with an increase in size of the footing. So the same case in case of the sand also. So it is essential to take into consideration both shear failure and the settlement criterion together to decide the safe bearing pressure in clays. While in sand, it was dominantly only the settlement, unless otherwise the footing size is extremely low, that is below 1.2 meter. But in case of the clay, regardless of the footing size, you should give importance to both shear failure, that is soil failure, and the settlement. So whichever gives the least bearing capacity, that would be considered in case of the clay soil. So footings on stiff clay, hard clay, and other firm soils generally require no settlement analysis. So if design provides a minimum factor of safety of 3 on the net ultimate bearing capacity of the soil. So soft clay, compressible silt, and other weak soils settle even under moderate pressure, and therefore settlement analysis is necessary. So these are a couple of the most important points with regard to bearing capacity when you are dealing with sandy type of the soil or clayey type of the soil. So relatively dealing with the sand is easy, but when you talk about the clay, you must be extra cautious because in sand there are no varieties. But if you look at carefully, so when you are dealing with the clay, you can see variety of clays. There is a stiff clay, there is a hard clay, there is a firm soil, then there is a weak soil, compressible silt, collapsible soil, soft clay, so on and so forth. So every clay must be dealt in a unique way, and this is the reason. So construction of any foundation on clay soils is a very tough task. So most of the time, most of the situations, one can encounter some kind of the failure when you try to deal with foundation design in clay soils. So that's why people normally will say, so if you are constructing something on sandy soils, it's like a bone. But something constructed on clay soils is a really daunting task. It's very challenging. However, but the entire foundation engineering lies in taking such challenges only. If you simply construct any footing with no challenge, there is nothing. Okay, so I now request you all, so take a pen, paper and calculator. So for tutorial, so now let us start tutorial on. So what are the concepts that we have discussed on the bearing capacity? So try to note down this problem and try to recall the equations which we have proposed or which we have discussed with regard to Terzaghi's theory, Meyerhoff theory, Hansen's theory, and Wissig theory. And let us try to understand how to determine or get a first-hand knowledge on how to determine the bearing capacity of a soil. So just note down, everyone. So a spare foundation is 2 meter by 2 meter in plan. The soil supporting the foundation has a friction angle of phi dash 25 degree and she dash 20 kilonewton per square meter. The unit weight of soil gamma is 16.5 kilonewton per cubic meter. Determine the allowable gross load on the foundation with a factor of safety of 3. Assume that the depth of foundation DF is 1.5 meter and that general shear failure occurs in the soil. So I request everyone note down this sum and try to solve using the equation. So in a first step you can follow the Terzaghi's theory. So anybody can tell me what is the equation of Terzaghi's theory? Hello.
Sir, it is a function of NC, NQ and N gamma.
Yeah, but what is that equation? That is a function true.
Sir, C into NC plus gamma DF
Yeah, so
NQ.
CNC plus QNQ plus half gamma B N gamma. So first note down that equation. So everyone note down this equation. Yeah, Aditya Verma. So let me call one by one. Are you there or no? Abhijit Kumar.
Yes, sir.
Yeah. So can you start? Arun. So majority of the people are simply logging in and going somewhere. Ashish Dev.
Yes, sir.
Yeah. So can you tell me what is the equation?
Wait, sir. Telling, sir.
Yeah, okay, okay, no problem. So those who knows the equation, so please try to substitute everything. Now, as I told, in bearing capacity equation, suppose if you look at the Terzaghi's bearing capacity, it is CNC plus QNQ plus half gamma B and gamma. Your NC, NQ, and gamma are the bearing capacity factors, which are functions of the angle of internal friction. So here a small table has been given. So this is NC, the first one. This is NQ. Okay, so the last one is called as a N gamma. So given pi dash is 25 degree. So corresponding to 25, NC, NQ, N gamma values are 25.13, 12.72 and 8.34. Banu Meena, are you there? Bandaru Akshita,
Sir, but here the depth of the foundation is not given, sir. Then how to take DF?
it's given 1.5 meter. DF is 1.5 meter.
Okay, sir. And sir, we have to take both gamma as 16.5.
Yeah.
Below
So,
and above.
yeah. So nothing has, since nothing has been mentioned about the groundwater table, so ignore the effect right now. Bhavyasri,
Yes, sir.
yeah. So can you try to solve?
Sir, I got 955 kilonewton per meter square.
Oh, great. Good, good. Can you explain how did you do it?
Sir, I just substituted that values in that formula.
Ah, fantastic. But one thing, so when we did discuss about Terzaghi's equation, the equation primarily valid for the strip footing. So for a square footing, it is a different equation. Please look into that one. That is
Okay.
only the small correction you need to implement it.
Okay.
Gaurav Pandey, Venkata Nagsai
Yes, sir.
Chaitanya,
Yes,
are
sir.
you there? Are you there?
Yes,
Very
sir.
good. Very
Yes,
good. Very good. So did you calculate?
sir. I am calculating. I am substituting the values in the equation, sir.
Okay.
It's coming out
So
1430.
okay. Very good. Rutvik.
Yes, sir. I'm substituting, sir.
Okay. Do it. Raviteja.
Yes, sir, I'm there. Substitute value. I'm calculating
Yeah.
from the calculator.
Okay. Do it. Do it. Very simple and straightforward. Okay. So let me show you the answer. So this is the equation. This is Terzaghi's equation, valid only for the square footing. Okay. So this is valid only for the square footing. 1.3 CNC plus QNQ plus 0.4 gamma B and gamma. So usually the general equation is CNC plus QNQ plus half gamma B and gamma. But the same equation was modified to be valid for the square foundation as 1.3 CNC plus QNQ. Your Q is nothing but overburden term. That is nothing but gamma times of df. So gamma is given as 16.5 kilonewton per cubic meter. DF is 1.5. So this is 16.5, while DF is 1.5 meter. So everything is known. And
Sir,
gamma
this 1.3 factor is only for square footing.
correct, exclusively for the square footing.
Sir, what will happen if this will be a rectangular footing?
If it is a rectangular,
Yes, sir. Suppose it is 4 by 2 or 2 by 4 like that, or
so
3
then,
by 2, 2 by 3.
then instead of this 1.3, there will be some other equation, maybe 1.2 or 1.4, something like that.
And how what to take B, sir?
Which one? E.
Sir, B value, sir, B. In square we are
B.
taking it 2.
Watch it.
Then what about in rectangle?
In rectangle, whichever is the smallest dimension.
Okay.
Sir, there was a formula for NC of square footing only. Sir,
No, you
won't
forget
use it.
about all those things. There are a variety of equations available for NC, NQ, and gamma. You simply follow this table. That's it. Because these values were calculated based on those equations only.
Sir, but it is differing a lot.
It cannot.
Previous formula.
No. There is no specific formula of NC pertinent to the square or something. So these NC, NQ, N gamma are pertinent to Terzaghi's theory. Okay, for example, if you look at Skempton's theory, then the equation for NC, NQ, N gamma are different. Most likely you must be seeing Skempton's theory. I don't know. So let me show you where is that. Skempton's theory. This is what are you looking at?
Yes, sir.
So this is valid for the Skempton's theory, as I told you.
Okay.
Okay, so what we are discussing is a Terzaghi's theory. Actually, these equations nowadays nobody is using. In fact, even Terzaghi theory is nobody is using. What we are using is only the Meyerhof theory. Okay, so NC, NQ, and gamma. So for a given pi dash of 25, NC is 25.13, NQ is 12.72, and then gamma is 8.34. So next, simply substitute everything into that equation, that is 1.3 CNC plus Q, that is gamma DF into NQ plus 0.4 gamma B and gamma. So then what we get is three different terms. The first one is called as a cohesive term, the second one is called as a overburden term, and the third one is called as a self-weight component. And summation of these three is the ultimate bearing capacity of the soil. Now usually one particular thing also you can notice, always the cohesion component is higher than the overburden component, which is always higher than the self-weight component. So this is the order. So this is one of the reason in couple of the books you may be saying that the last term is simply ignored because this value is usually very low, while the preference is given only for the first term in majority of the books also. So don't think otherwise if you are encountering such thing. Okay, then one important thing is there are two different terminology. One is QU, that's what I told, ultimate bearing capacity of the soil. Next is Q allowable, That is allowable bearing capacity of the soil. So these are the two important things you must remember. Ultimate means, suppose you try to distinguish between the ultimate value of 107978 kilopascals and 359 kilopascals. Now what is the meaning of these two? So the fundamental meaning of these two is that if we apply a stress of 1078 kilopascals, behind this value the soil fails. The soil fails. Okay. Now what is the meaning of 359? I can apply a stress up to 359 kilopascals safely. Now here what do you mean by the safe? If I apply this much amount of the stress on soil, my settlement is within the permissible value. Say that is 25 millimeter. So my settlement will not exceed 25 millimeter. So that's what is the meaning of ultimate and allowable. So this everybody should understand.
Sir,
Yeah.
so how can you know like which equation should be used when like here we have used Terjagi, why can't we use Meyerhof equation, sir?
You are most welcome to use it. So I'm taking one by one. So this is very simple equation. So therefore I'm demonstrating. But for the same sum, you can also use the Meyerhof equation.
Okay, sir.
Okay. So that part also I will take care. So is this problem is okay? So any questions? Any questions from this sum? Now you are asked to calculate the allowable gross load. Remember, this is allowable stress. Next, allowable load. So if you want to calculate the allowable load, simply multiply the allowable stress with the respective area. So in our case, it is a square footing. So that is B square, 359.5 multiplied by 2 into 2. So 1438 kilonewton. So here, one important thing is that, see, this is the footing. This is the footing which is located below the ground surface. Below the ground surface. Now there is a soil beneath it. Okay, so below the footing there is a soil. And so, and there is a footing also here. The load is coming from the footing simultaneously. The load is also coming from the footing. And the load is offered by the soil is also there. So what we calculated, this 359, indicates the load resistance offered by the soil. It is not equal to the load coming from the column. So this is the column. Remember always, what we are going to deal with is only the soil component, not the footing component. So the footing component is belong to the structural. Now once I know the allowable bearing pressure of the soil, then I will recommend the same value to the structural engineer. Then accordingly, so he will design the footing size. Okay, but here the controlling factor is soil, not the structure. Not the structure. Okay, so the difference between, say, this is QU and this is Q. So the ratio between these two is also called as a safety factor. So factor of safety, same thing you can understand from here. If you take the ratio of QU by Q, so I can say QU by Q column. QU by Q column, then that is also called as a factor of safety. So here suppose you are giving importance to only structure, ignoring the soil. If QC is higher than QU, then the soil fails. That means entire structure fails. So most of the time people will ignore this small simple verification. If you look at any report, so this will be given the least importance. You should not do that part. You always taken into account of the soil condition. So there is always compromise on the structure. Suppose if you do not want to compromise on the structure, where say for example your QC is say 1000 kilopascals. QC is 1000 kilopascals, but the QU of the soil is only 359 kilopascals. Then what shall I do? So the obvious choice is, in order to improve the value of the QU, then you have to go for the ground improvement. You have to go for ground improvement. Now we cannot directly go for the ground improvement. So first thing is that means your so thought process should go like this. First, your column load or column stress is 1000 kilopascals. The bearing capacity of the soil is 359 kilopascals. So you try to play with the geometry of the footing itself. If I increase the size of the footing, can I get higher factor of safety or higher bearing capacity? Even if that is not possible, then the next alternative is, instead of going for the shallow foundation, then go for the deep foundation. So that means you are discarding the footing, then you are going for the pile foundation. Suppose even after adapting to the pile foundation, you are still the bearing capacity of the soil is less, then you must go for the ground improvement. So this is how the school of thought goes. Okay, yeah. Now the same thing in a reverse way. Same example, note down this one, refer to example 4.1. So that is given above. Assume that shear strength parameters of the soil are same. A square foundation measuring B by B will be subjected to an allowable gross load of 1000 kilonewton with factor of safety of 3 and DF of 1 meter. Determine the size B of the foundation. So it is simply reverse of the above problem. So in the above sum, we know the geometry of the footing and we know
Sir,
yeah.
sir, in last question, what is significance of this last part that general shear failure occurs? One assumption is.
Oh, acha, that one. General shear failure means, if you remember in the second class, as per Terzaghi, there are three variety of the failures: general shear failure, local shear failure, and punching shear failure. In shallow foundation, punching shear failure will not happen, while there is a probability of general shear failure and the local shear failure. General shear means where the failure plane is extended up to the ground surface, and in local shear failure, the failure is confined below the ground surface. Now suppose if you are asked to calculate based on the general shear failure, what we have done is exactly falls under the category of general shear failure. In case of the local shear, this C, suppose if you are asked to do for local shear, this C must be taken as 2/3 of C. 2/3 of C dash for local shear. Similarly, pi dash is 25 degree in this case. For local shear, so this again shall be calculated as, so pi dash is tan inverse 2/3 of tan pi. 2/3 of tan pi. So this is valid for the local shear. This is valid for the local shear. Okay. Now by doing so, what you are doing? You are little bit underestimating the value of QU. It's very simple to understand. Say for example, under general shear condition, the pi dash is 25. Now under local shear condition, how much this will become? Can you calculate and tell me? Can anybody calculate tan inverse 2/3 of tan pi and tell me the value of pi dash for local shear?
17.273.
Okay. So this is a local shear. 17.27, approximately say 17. Okay, 17. Now earlier what we have done, we have taken NC, NQ, N gamma for corresponding to 25 degree. Now the NC, NQ, N gamma shall be taken for 17 degree for local shear. Now see the difference. When I have taken 25, NC is 25, NQ is 12, and gamma is 8. But when I take 17, NC is 14, NQ is 5, and gamma is 2. Okay, so almost 2/3 in the reduction of the value. So as a result, there is a gross reduction in the value of the QU. Gross reduction in the value of the QU. So in this case, we got approximately 1075 kilopascals as the ultimate stress under general shear condition. Now, if you repeat the same thing for local shear condition, you may get around 950 or 900 kilopascals. So you can repeat the same thing, no problem. So did you understand the difference between general shear and local shear?
Yes.
Okay. I will also take another example on the local shear just to avoid the confusion. No problem. Yeah, note down this sum. Refer to example 4.1 above. So the shear strength parameters are same. But here the allowable gross load on the footing is 1000 kilonewton. So you are asked to design or suggest the size of the footing. In the earlier case, we were going from bottom to the top. Now this is coming from top to the bottom. If you know the stress coming from the column, then you should design the footing size.
Sir, 1.77 meter.
1.77 meter. Very good. Others, please.
Sir, just equating the allowable load is equals to 1000.
Yeah, just look at here. So here allowable load is given, capital Q. Okay. So ultimate not known. Ultimate you need to calculate. B square is unknown. You look at these equations. Capital Q has been given as 1000 kilonewton. Q ultimate or Q allowable you need to calculate. And B is unknown. Simple this equation only. Bas. So allowable gross load is 1000 kilonewton with a factor of safety of 3. Hence QU is 1000 multiplied by 3, that is 3000 kilonewton. 3000 kilonewton. So QU is equals to capital QU by B square. Because this is same equation. Some problem number 1. So the ultimate bearing capacity is nothing but load by area. Load by area. So but here area is
That
unknown.
is 1.68 something.
Okay, very good. But I hope you understood the logic now. How to calculate the width or size of the footing.
Yes, sir.
So the equation for QU is same now. I know the capital Q. Now I can able to calculate the small QU, ultimate bearing capacity for square footing. That is 1.3 CNC plus QNQ plus 0.4 gamma B and gamma. Here only difference is in the earlier sum, DF is 1.5 meter. Now in this case it is 1 meter. and pi dash is 25. So take the values of pi dash 25 and C and Q and gamma. So then Q is equals to gamma into df. So 16.5 into 1, 16.5, and substitute into this QU equation. Again here also B is unknown. So C 1.3 C and C, 1.3 into C is 20 and C is 25.13 plus Q is 16.5 and NQ is 12.72. 0.4 gamma is 16.5, B is unknown, 8.34, that is N gamma. So you will get another form of equation 863.26 plus 55.04 in terms of B value. So substitute same equation or equate. So 3000 by B square is equals to QU, which is nothing but 863.26 plus 55.04 into B. So then simplify this equation, then what you get is B value. So approximately 1.8 meter. So we have now seen two cases. One is forward case, where if I know the soil property such as C and pi, then I understood how to calculate the ultimate bearing capacity of a soil. The second one is, so if my structural engineer is giving a column load, then I have calculated what should be the minimum width of the footing required. Now this is one of the simplest one. How can I make this is bit complicated?
Sir, this is square, na sir.
Yeah, this is square.
If you don't give any shape, then it will become complicated.
Suppose if you also introduce L term, then what happens? So your QU by that becomes L by B. Okay, so L is unknown, B is unknown. So two unknowns, one equation. So I can even further make complication by not giving DF value. So here what we need to do is keep on assuming one value. So assume initially DF of some value and length of some value and keep on calculating the width, or assume width and calculate the length, whatever it is.
Sir, for circular footing, we have to take B as the diameter of the
Correct.
footing.
Correct. Harshvardhan, Meena?
Yes, sir.
Yeah, so did you calculate?
Yes, sir. Last one is right. 1.67.
1.67. Okay. Very good. Rohit?
Sir, 1.65 is not correct, I think.
How much you are getting?
Sir, basically we get 1.65 if we assume QU is same like that of previous question.
Okay, no issue. That's because in the previous sum, the DF is 1.5 meter. In this sum, DF is 1 meter. So obviously we'll get smaller value. Okay, so let me ask you a question here. Now here the footing is located at a depth of 1 meter from the ground surface. So what will happen to the bearing capacity if it is shifted to the ground surface? What will happen to the bearing capacity?
Sir, bearing capacity will become very less.
Bearing capacity will become very less. So can you explain so that
Sir,
others also
that
can
term, sir, overburden term will be zero, na sir?
correct. Suppose if the footing is on the ground surface, so let us look at gamma times of df. If it is on the ground surface, this will become 0. df is 0. That means your entire q and q will become 0. The whole second time will be absent. Okay, so that's how there is a drastic reduction in the bearing capacity if it is shifted from below ground surface to the above ground surface. Now my another question is, what will happen to the bearing capacity if I increase the width of the footing?
It will increase.
It will increase because the width is inbuilt in the third term. It is of gamma b and gamma. So as you increase the width of the footing, so there is increase in the bearing capacity. Okay, that means your bearing capacity equation includes the soil properties, that is C and pi, geometry of the soil, the geometry of the footing, that is B, then overburden term, that is Q, and another soil property is density. So anything means if you change it, so then obviously there is increase or decrease in the bearing capacity. Okay, now this is circular footing. So let us try to repeat the same thing. Determine the allowable bearing capacity of a circular footing of 4 meter diameter and bottom of footing at 5 meter below ground level, provided with a factor of safety 3.5. The foundation soil as C 20 kilopascals and pi 30 degree and unit weight 12 kilonewton per cubic meter. So use Terzaghi's analysis. Okay, so this is also very simple sum. So nothing is talking about the effect of the water table or general or local shear condition. Assume no effect of water table and it is a general shear failure. So what is the equation for circular footing? So this is the given data.
Circle the remaining everything is same, sir, like square footing is
Except
L5 term is 0.37.
okay. So that means it is 1.3 C and C. So 1.3 C and C plus Q and Q plus 0.3 gamma B and gamma. So your first step is pick up the values of bearing capacity factors, that is NC, NQ and gamma. So for a given pi of 30 degree. So from the table, and again I repeat, these values will be provided in the exam. Either direct values or the necessary table will be provided. So from that table in the exam, you must pick up the values of NC, NQ and N gamma. So if you have any question, you please ask right now. How to pick up the values of NC, NQ and N gamma. Now you also must have observed, as the pi value increases, so does the values of NC, NQ and gamma. In the previous sum, the pi was 25, but NC was 25, NQ was around 12 and gamma is around 8. But as we are increasing the pi, so from 25 to 30, you can also see there is an increase in the values of NC, NQ and gamma. So this is how the bearing capacity also increases. So this is the equation. The ultimate bearing capacity QU is 1.3 CNC plus gamma D and Q, that is Q and Q plus 0.3 gamma B and gamma. So can anybody tell me answer? Maunika? Vemula Maunika? She was not available in the... You are there? Yeah. So can you please tell me the answer? Kalyan? Vadapalli Kalyan? Trilok Sinde?
Sir, QU is coming 258.92.
258.92.
Yes.
Good, good, very good. Tanjib Ahmad? So this is the final answer. QU is 1.3, C is 20 and NC is 37.2, gamma 12, D is 5 meter depth and Q is 22.5, 0.3 gamma, B is 4 meter and N gamma. So total
Sir,
is, yeah.
here the overburden term is greater than that of cohesion term, sir.
Overburden term is, okay, no problem. That's because of your depth is very high. That's because your usually depth of DF of 5 meter is very rare. That is the reason it is high. Okay, so if you calculate everything, the ultimate bearing capacity is 2600 kilonewton per square meter. since a factor of safety of 3.5 need to be imposed, so 2600 by 3.5. So we can allow the soil bearing capacity up to 743 kilopascals. 743 kilopascals. So allowable soil bearing capacity is 743 kilopascals. So 2600 minus 743, that is a margin. So that is accounted for any kind of a future failures. Yeah, others. Let me touch upon Satish Kumar. Sundi Satish Kumar. Not available. Shivam Kumar.
Yes, sir.
Yeah. So did you calculate?
You're doing it in my copy.
You're still doing it. Okay, very good. Do it, do it. Please do it and let me know the value. Abdul Arshad.
Yes, sir.
Yeah. So did you calculate?
Yes, sir. Till now I have calculated, sir. The 2600 and 739. Till there I have.
Okay, very good. Sanket.
Yes, sir.
Yeah. So did you calculate? Any questions?
Sir, Q ultimate is 2600.8, sir.
Okay. But any questions?
No, sir.
Did you understand everything?
Yes, sir. I'm calculating aloud, sir.
Okay.
Q aloud.
Very good. Sweta.
Yes, sir.
Yeah. Any questions?
No, sir, I have calculated.
Okay. So any difficulty in understanding?
No, sir.
Very good. Sagar Singh Rathod.
Yes, sir.
Yeah. So everything is fine or any difficulty in somewhere?
No, sir. Fine.
Fine. Very good. Vinay Kumar.
Yes, sir.
So did you calculate?
Yes, sir. I got Q allowable equal to 742.85, sir.
Very good. Which otherwise any questions from the bearing capacity?
No, sir. No, sir.
Okay.
It's all good.
Romit Kesharwani.
Yes, sir. Sir, I got, sir. Bearing capacity is 743.
Okay, very good. Yeah, you are doing fine, fine. Shiva.
Yes, sir.
Yeah. So did you calculate? Any other question
I'm
that you would like to
doing
ask?
bearing capacity.
Okay. But do you like to ask any question?
No, sir.
Priyansh Shoria.
Yes, sir.
Any difficulty?
No, sir.
Very good. So Priyansh Nigam.
Yes, sir.
Yeah.
Sir, I got bearing capacity as 743.1 and allowed load as 9,338 kilonewton.
Okay, very good. Any other question you would like to ask?
No, sir.
Very good. Prakash Shooter.
Yes, sir. Sir,
Yeah.
sir, I got bearing capacity 743.1.
Okay. So, will you like to ask any question?
No, sir.
Okay. So, let me give you another sum. So, in the meantime, you can able to calculate. Yeah. So, just note down. So, this is the effect of the groundwater table. A footing of 4 meter by 4 meter carries a uniform gross pressure of 300 kilonewton per square meter at a depth of 1.5 meter in a sand. The saturated unit weight of sand is 20 kilonewton per cubic meter, and the unit weight above the water table is 17 kilonewton per cubic meter. The shear strength parameters are C-0, pi-32. Determine the factor of safety with respect to shear failure for the following cases. The water table is at ground surface. The water table is 1.5 meter below the surface. Okay, so everybody please note down. So this problem is addressing the impact of water table. You are asked to calculate the factor of safety with respect to shear failure when the groundwater table is at the ground surface and when the groundwater table is at the foundation level. Here in this case, because DF is 1.5 meter, which perfectly matches with the foundation level. So for case A, which term gets impacted? Among the three terms, so which are the terms gets impacted if the groundwater is at the ground surface? So let me show you those slides better. You can
Second
understand.
term.
Yeah. You can understand now. In our sum, we are calculating for case 1, where groundwater table coincides with ground surface, and case 3, where groundwater table coincides with foundation level. Okay, so case 1 and case 3. If you refer to some of the books, not in this manner, but they have taken into account the groundwater table in a different way. But this is I found is easiest way of understanding the effect of groundwater. So you can follow either this concept or the other concept which you found in other book. Both are equally valid. So don't get confused. Suppose if you look at IS code, the groundwater effect is given in the form of a parameter called as a RW. Capital RW. So meaning of the both is same. Either you follow this concept or you follow RW concept. Both will give you the same value of the bearing capacity. So in the first case, which term will get affected?
So both overburden term and that footing term last term.
Yes, fantastic. And in the second case?
Sir, only that bottom one.
Only the self-weight component.
Mm.
So anybody could able to solve?
Sir, what are the values of NC and QN?
Okay. So let me give the solution. So this is the equation for the factor of safety. Both are same. Okay. So this is another way of writing the factor of safety. Q ultimate net divided by Q net. So or Q net QNF by QN, or the same thing can be rewritten as Q ultimate net means Q ultimate minus gamma df. Now here, what do you mean by this? What do you mean by this minus gamma df, which is nothing but this term up to a depth of 1.5 meter. So in another way, before the construction of the footing, the entire soil is excavated up to a depth of gamma times of dm. That means you are removing this much amount of the overburden, and at the same time, once footing is constructed, you are refilling the same amount of the surcharge load. Suppose if you want to account for such a removal and recompaction of the soil, the same thing is rewritten in the form of a net or net ultimate. So here Q ultimate net matlab, net means Q ultimate minus gamma df, and Q net means Q gross minus gamma df overburden. Okay, so this can also be written as in this form, Qf minus gamma d by Qn. In whatever the form you understand, so there is no problem. Or you can directly use the another factor of safety equation. So this is the square footing. This is the equation for the square footing, and these are the values. For pi dash of 32, just remember, in this sum, the value of the cohesion is 0. Cohesion is 0. So therefore, this entire cohesion term becomes 0. Entire cohesion term becomes 0. So the only term remaining is pi dash, n gamma and nq. N gamma and nq. Your nc is, you don't need to take it. Even if you take the value, that whole thing will become 0. So pi dash 32. And here also given your Q ultimate is nothing but QF. Q ultimate is nothing but QF. So first try to calculate Q ultimate. Now here, if you take case A, this gamma will become gamma dash, and this gamma also will become gamma dash, gamma submerged, because the groundwater table coincides with the ground surface. While in the second case, so only the third term, the self-weight component gamma, becomes gamma dash, and the overburden term gamma will remain as gamma only.
Sir, we can simply do na, sir, factor of safety is equal to Q ultimate upon Q allowable.
Yeah. That's most welcome.
Oh.
Yes. So first you calculate Q ultimate. So what we get is 851 kilopascal. This is for the case A. And here you can see gamma is replaced with the gamma dash. Gamma is replaced with the gamma dash in both the terms. So overburden term and self weight term. And accordingly you can see 20 minus 10, 20 minus 10. That is submerged unit weight of the soil. So then Q net ultimate is nothing but Q ultimate minus gamma dash D. Gamma dash D. So this is 836. On the other hand, Q gross has been given in the sum directly. So that is 300 kilopascals. Okay. So Q gross has been given, that is 300 kilopascal, and Q ultimate has been calculated as 836. So the factor of safety, so Q net is nothing but Q gross minus gamma df. So your factor of safety is Q ultimate minus QF minus gamma df, that is Q net allowable divided by Q net.
Sir, what is QF and QNF?
Both QF and QNF. Here you can see QF is nothing but Q ultimate. Sorry, ultimate. QNF means net ultimate. You can see Q ultimate net. That is
Sir, but
Q
in
ultimate
case of
gamma.
factor of it is ultimate upon allowable, no sir. We don't take net ultimate like that.
No, see, if you are taking ultimate minus gamma df, at the numerator also you should take gross minus gamma df. That's what here it is taken. In fact, you can directly
do no sir without subtracting gamma d from numerator.
That's what I'm saying. Na. You can directly
sir,
take.
But answer will be different, na, sir.
How much you are getting?
Sir, for first one I am getting 2.9.
It's okay. 2.9, 3.1. It's marginal.
Oh.
Excuse me, sir.
Yeah.
Sir, in the above equation, like you have written QNF is equal to QF minus gamma dash D.
Yeah.
But in the factor of safety, we have to use gamma D or gamma dash D, like in the final QF minus gamma D. It should be QF minus gamma dash D, no?
No, here it has taken care. Now you look at. So QNF is QF minus gamma dash D. It is shown already here in both the cases.
Okay, sir.
Sir, but here, sir, for calculating Q net, it is taking, sir, in first case, it has taken 300 minus 20 into 1.5.
That's why the second case also shown. Na?
Sir, what is that second case? I didn't know.
You take first case, that is 300 minus gamma df.
Sir, but in above for calculating QNF, it is taking gamma dash D. But in here, factor of safety equation both are written as gamma D, gamma D.
That is because, see, the first term, this term belongs to the soil component. Okay. So while this term belongs to the structural component. You try to understand. The above term belongs to the soil component. You are exclusively dealing with the soil bearing capacity. While Q gross is something coming from the column load. Okay, so there you are accounting for the grass column load. You don't account for change in the soil weight, whether water table or no water table doesn't matter. So that's why I have simply taken total grass weight. So net means grass minus again grass.
Sir, then what is the second part? Minus 1.5 into 10 minus 1.5.
So this is another way of rewriting the same thing. Here only height changed 1.5, 1.5
Oh,
up to below the ground surface. You can neglect this second case. You can consider only the above one. If you look at carefully, so here this is a grass calculation. Here the same thing is, see, they converted this also into net minus net. So this accounts for, this is weight of the water, 300 minus weight of the water, and this is submerged weight of the soil. Submerged weight of the soil. While here this accounts for both weight of the total weight, grass weight. Anyhow, I will stop it here. It's already 11:02.